Hey guys, Mr. Patman today is going to teach something that you guys wait for so long. I'm going to teach something out of your syllabus in your class. Thanks. Okay, today I'm going to introduce you guys something that is the fastest in our universe. Oh, sorry, on land. Okay, it is
Maglev. So, this list below is the few main things that we are going to discuss today. First is the introduction of Maglev Train. Second is the physics law that relate to Maglev, which included Faraday's law and Lenz's law. Third is the working principles of magnetic train, which has electromagnetic suspension, which is EMS, and electrodynamic suspension, which is EDS. We are going to talk about differences between EMS and EDS, and also the advantages of Maglev, and last but not least, the modifications of Maglev concept for future use. Magnetic levitation train or magnetic suspension train. Maglev is a super high-speed transport system which it has modified railways, and the train itself has not equipped with wheels. This is how it looks like. Maglev move by levitation and propulsion, which later we are going to talk about this more in detail. On the other hand, Maglev is a combination of superconducting magnet and linear motor technology. What is superconducting magnets? It is a magnet which will experience zero resistance when it is below its critical temperature. This highly increases the efficiency of Maglev train and reduces energy loss.
So Maglev means magnetic levitation. Maglev.
Okay, so how does a Maglev train work? It basically depends on magnetic levitation and propulsion. And simply levitation means float, and propulsion means propel forward. So in this case, it means by lifting something and propelling it forward by magnetic field with the presence of flowing current and with no other support. It also counteracts the effects of gravitational accelerations and any other accelerations, which means by that gravitational acceleration is a acceleration towards the Earth, where when it's counteract means it opposes the effect.
Now, we are going to talk about the two physics law that relates to Maglev. First is the law that induced by this handsome guy, which is Mr. Faraday. And the second law, which is induced by this handsome guy also, which is named Mr. Lenz. Faraday's introduced Faraday's law, and definitely Lenz will introduce Lenz's law. Okay, very simple. Now, we are going to look at the Faraday's law, and you see the definition here. Did you see this? When there is a change of magnetic flux, the induced EMF will produce. After reading this, I am sure that you guys don't know what's happening here. Maybe some of you know, but never mind, I will show you in a better way. Let's look at the marvelous definition of Faraday's law. Actually, what Faraday's mentioned can deduce from this mathematical equation. It is very simple. Look at this. We have epsilon equal to negative d phi over dt, and you guys should know that epsilon is the EMF, or usually we call it electromagnetic force, and we have a phi here, which is a magnetic flux, or sometimes we call it magnetic field line, and which pass through the circuit, and t is that you guys must be familiar, which is the time. So we have an epsilon here and a phi here and a t here. So now look at it. Now we have a d phi, which is the differentiation equation. D means the difference of magnetic flux. Phi is magnetic flux. And indifferent, also we can call it the change of magnetic flux. And here we have dt, which is the change of time, or in something in physics that we divide by t, we call it rate of something. So if you combine these two sentences into one, you see that actually the d phi and the dt will become the rate of change of magnetic flux. And what happened was epsilon, which is EMS, equals to what? When there is a rate of change of magnetic flux, it will produce the induced EMF, which is the epsilon. Yay! Now, let's look at the previous slide. The Faraday's law states that when there's a change of magnetic flux, the induced EMF will be produced. And the change of magnetic flux according to the mathematical equation is just the d phi over dt, and the induced EMF is just the epsilon. It's just that simple, right? Okay. Now, we're going to talk about the Lenz's law. What is the Lenz's law? Actually, Lenz's law is what I didn't mention, which is the negative sign that in the Faraday's law of induction. It's just as simple as that. Have any one of you think of why the Lenz's law is shown in the negative sign of the Faraday's law? Let's look at the definition to have a clearer picture. When an induced EMF is produced by the change in magnetic flux, this is simply the Faraday's law of induction that we just learned earlier. And the polarity of the induced EMF is such that it produces a current whose magnetic field opposes the change. The polarity, which is N or S, the N of S, which is opposes the change which produces it. Meaning, if the magnet that produces it is an N pole, and then in the solenoid it will produces a south pole which will opposes the pole that produces it. Because of the change of direction, according to vector quantity, and the d phi is a vector quantity over dt, and we forget the epsilon, if there's a opposes the direction of the thing that produces it, which means it is not the original direction but the opposite direction, that's why we add a negative sign here, which signify the opposite direction. That's why Lenz's law is shown in the negative sign of Faraday's law. But how we determine the magnetic field of the current produces is opposes the change? Let's look at the image below. Now we are going to discuss about the first image here. When the north pole is moved in this direction, approaching the solenoid, the magnetic field line in the magnet will cut across the solenoid. This actually produces the induced EMF in the solenoid and also the induced current. Because the polarity of the induced EMF have to oppose the changes that produces it, the way to oppose the change is to produce a north pole in the solenoid that which will repel the original magnet that want to goes into it. And by using the right hand grip rule, we can determine the direction of the electric field. And this is the north pole, and the thumb will pointing at the north pole, and the finger will show the direction of the current, which is in this direction. This is how we determine the direction of the current flow and the polarity of induced EMF by using Lenz's law. After knowing the basic concept of the both laws, which is the Faraday's law and the Lenz's law, we now have to know how it relates to the levitation and propulsion of the magnetic levitation train. Now my friend Henry is going to talk about what is the two types of maglev train and how they work respectively.
The same magnetic pole will repel each other and different magnetic pole will attract each other.
Since then, China, Japan and South Korea have all joined the race to develop the fastest maglev systems. But what exactly is it that allows these trains to move so quickly? In short, the answer lies in electromagnetism. However, there are currently two very different systems of maglev that provide suspension in two very different ways. The first is called Electromagnetic Suspension and is used in the current German transrapid system. EMS uses the attractive forces between iron core, electromagnets, and ferromagnetic rails. Electromagnets that have current flowing through them are first placed on the underside of the carriage, which creates a magnetic field that is attracted to the stationary ferromagnetic reaction rails that are installed on the underside of the guideway. This attraction results in a distance of just 10 mm between the stator and support magnet, which allows the carriage to hover 150 mm above the top of the guideway. The train is propelled by the support magnets on the carriage, which provide an alternating current that works to create a series of attractive poles and repelling poles, resulting in forward movement. The second system is electrodynamic suspension and is currently used in prototype Japanese SC Maglev trains. EDS relies on the principle of superconductivity, whereby superconducting materials are cooled to extremely low temperatures. The superconducting materials are placed on the side of the train carriage and interact with figure 8 shaped coils on the side of the guideway. When the coils experience the changing magnetic field of the superconductor's motion as the train moves, two currents are induced that oppose the change in magnetic field. One below that creates a reactive magnetic field that opposes the superconducting magnet's pole, and one above that creates a pole that attracts it. Thus, the two forces work together to achieve an approximate levitation of 10 centimeters above the guideway. Propulsion is achieved by a linear synchronous motor consisting of additional coils in the guideway that provide a three-phase alternating current. The magnetic field created by the superconductor then interacts with this magnetic field to propel it forward.
One of the main differences between EMS and EDS
is that EDS uses superconducting electromagnets, so they have refrigeration problems. EMS, on the other hand, uses standard electromagnets, therefore there are no refrigeration problems. Another difference between the two is that EDS uses the opposing force between superconducting magnets on the train and electrically conductive strips or coils in the guideway to levitate the train. For EMS, the magnets attract up towards the laminated iron rails in the guideway and lift the train. It makes use of the attractive forces to lift the train as well as reduce friction. For EDS, the distance between the train and the guideway is around 10 centimeters. This system is stable and does not require continued monitoring. For EMS, on the other hand, the distance between the electromagnets and the guideway is about 10 millimeters. This distance must be continuously monitored and adjusted by computer in order to prevent the train from hitting the guideway. This system is unstable and would fail without this intervention. EDS also induces high-intensity magnetic field. Therefore, the passenger section of the train will have to be shielded from the magnetic field, or else it would be dangerous for passengers with pacemakers, and it may damage magnetic data storage such as credit cards and hard drives. The intensity of the magnetic field induced by EMS is low and comparable to the Earth's magnetic field. The advantages of maglev is that a maglev can travel a lot faster than conventional trains. Maglevs can reach speeds up to 500 km per hour, and the highest recorded maglev speed is 603 km per hour. Due to its lack of wheels, maglevs are quieter than normal trains. In theory, a maglev and its track would require very little maintenance. Since the train never touches the track, there is virtually no wear and tear. Maglevs also use 30% less energy as compared to normal trains, hence they are more energy efficient.
Maglev is a very advanced technology in the modern era. Therefore, a lot of modifications have been done using this particular concept for better future use. And some of the amazing and interesting examples include maglev cars, floating cities, and Skytrain. So the first one is the maglev car, and I think some of you might heard about it. So this idea actually came by during a challenge by Volkswagen for the China residents to draw out their idea of a future car. So this was the final concept taken and modified by Volkswagen, and it is based on magnetic levitation, which the car travels along electromagnetic road networks. So the interesting fact about it is that it can carry passengers up to a speed of 360 kilometers per hour. And it is a high-speed efficient transportation facility for future use, although it has not been proven, but someday it definitely will be. Okay, so the next one is the floating cities, which is also known as heaven and earth. So this is proposed by a Chinese architect named Wei Zhao, who was an honorable winner in a skyscraper competition in 2012. So it basically works when magnetic field is generated, it repels the gravitational force created by Earth and allows the floating island to remain suspended in air. It allows people to stay in an island floating on atmosphere quite far above the ground, where the air is free from any kind of pollution or impurity. Doesn't it sound amazing? So this idea came about because of the decreasing availability of ground on Earth due to increasing in population over the years. Okay, so last but not least, the Skytrain. Okay, so in my opinion, I think this is the coolest modification so far. So this is developed by an American company named Unimodal Transport Solutions. It is basically a two-passenger vehicle. It's a high-capacity and high-speed personal rapid transport system. It is propelled and suspended by maglev system, and it is laid out in a 1 mile by 1 mile grid throughout the city. So it has a large number of small departures or exit portals placed beneath the guideways, which is you can look here in the photo. And it is placed approximately every 400 meters or at every city block according to the concept. So in conclusion, I think magnetic levitation is undeniably an amazing and interesting technology with very big potential to build a better world. With this, it could be utilized in many daily life necessities ranging from transportation to household appliances and even decorations. And with the technology currently being expensive to implement, its potential value to be further explored has continued research. And further possible applications need to be explored for the sake of mankind.